Nous sommes réunis aujourd'hui pour assister à la soutenance du candidat صدقة Liyas qui va défendre une thèse de doctorat en mathématiques appliquées intitulée Généralisation des techniques de linéarisation pour approcher les systèmes d'équations intégrales non linéaires. Devant le jury constitué du professeur Carlos Raddin de l'université Mentori Constantine, du docteur Riyad Mourad, MCA de l'université de Galma, et docteur Belhirch Hanan, aussi MCA de l'université de Galma, et devant son directeur de thèse, professeur Aïssaoui, de l'université de Galma, et son co-directeur de thèse, le Meta Samir, MCA de l'école supérieure ENS Ouargla. Et devant moi-même, en tant que président du jury, le professeur Hamza Goubaï, Université de Galma. Allez-y, vous avez 40 minutes pour défendre votre thèse.
Merci, Monsieur le Président. Mesdames et Messieurs, membres du jury, honorables assistants, bonsoir. J'ai le plaisir de présenter ma présentation de ma thèse de doctorat intitulée Generalization of Linearization Techniques to Approximate Systems of Non-Linear Integral Equations. So let's begin by citing the different steps of this presentation. We will begin by an introduction, and we move to defining a new approach for solving nonlinear freedom integral equation systems, and we move to the efficient numerical scheme for nonlinear integral equation, the LDD-NU method. And we will solving also a system of weakly singular nonlinear integral equation using the LNDK new method. And lastly, we close with a conclusion. So, nonlinear system of integral equation of the second kind find application in various fields and offer a valuable idea in solving complex problems. They are useful in modeling dynamic systems such as population dynamics, electrical circuit, and biological process. These equations also find application in image restoration, signal processing, and data analysis. Additionally, they play a crucial role in mathematical physics, providing solutions for phenomena such as heat, conduction, fluid dynamics, and quantum mechanics. By studying and understanding these systems, we gain powerful tools to analyze and address complex real-world problems in multiple disciplines. So, in general, nonlinear functional equations are sitting as the following form: f of c equal 0. So, solving this genre of equation analytically is almost difficult and impossible. For this reason, we move to the numerical methods. So, because our problem is sitting in the infinite dimensional context, so for this reason, we need to make it in the finite dimensional context, and because it's non-linear, we also need to make it a linear problem. So, for this reason, classical numerical methods beginning by a discretization phase and move to the linearization phase. In this point, we pose the following question. Which one should we begin with, linearization or discretization? So, a recent published paper confirmed that beginning by the linearization phase and move on the discretization phase is the better process. So in this diagram, we will show the difference and the main steps to construct the LD new process, linearization, then discretization, and we will show also the main steps to construct the DL, discretization, linearization, classical process. So we can see clearly that the approximate solution obtained by the LDU process, psi and phi k plus 1, is converted to the exact solution obtained by the LDU process for a fixed n and k tend to infinity. Unlike in the another hand, for the DL classical process, where we need to tend the path N and K to infinity to obtain the convergence. So we start with the first part, when we will define a new approach for solving non-linear freedom integral equation systems. So let's sit in our problem as a non-linear integral differential equation. So for solving this kind of problems, we choose to transform this equation to a system of integral differential equation. So by setting the following notation, problem 2 will be converted to a system of integral differential equation presented in system 3. This system also will be writing in the general form of nonlinear functional equation, f of c equals 0, to be able to apply the LD new process with the following notation of psi, g, and the operator k. So to solve problem 4, we propose applying the new LD process as the following manner, where for the linearization phase, we will apply the Newton iterative methods, and for the discretization phase, we try to apply the Nystrom method to estimate each operator, nonlinear integral operator obtained by the first stage in our linear problem obtained by the linearization phase. So, firstly, we said that we need to apply the Newton iteration process to get the following linear scheme, where the empty here is the Frisch derivative operator for our integral Frisch derivative operator K, and it's given by the following formula, where each element of this block matrices operator is presented by the following expression. Now we need to assume our condition for use it in the convergence analysis of our approximate solution. So we choose to use to propose that we have a unique solution, and we must also propose that our block matrix operator EM minus MT in the exact solution is invertible, and its invertible operator is bounded. So the discretization of the scheme 5 is presented as the following form, where NTN is the approximate block matrix operator out of the block matrix operator MT, and is given as the following form, where for all EG, we have the TNEG is the natural approximation of the linear operator TEG, and the delta N is the subdivision equidistance of the interval 0, 1. So we can also write the scheme Cs for all E take value between 1 to m as the following form. So solving this system 7 and 8, we must pass by 2 steps. In the first step, we need to solve the linear algebraic system, where for all EG take value from 1 to m, our matrix is AK, and the second-hand part of this linear system BEK, given by these formulations. And EM is the real block matrices given by the following values. So for the second steps, we need to recover our approximate solution C phi n e k plus 1 by the natural interpolation formula as follows. And here we see clearly that we use the result of the resolution of the linear system to recover our approximate solution. Now, before studying the convergence of the approximate solution gotten by the LNDN new process, we give some properties that is important to prove our main convergence theorem. So we need to demonstrate, and we demonstrate that the MT is lambda R Lipschitz over the neighborhood of the exact solution with the radius R. There exists a constancy M such that the norm of MT and the approximate block matrix operator MTN is bounded by Cm over n squared. We also need to prove that the block matrix operator Em minus Nt is invertible, and its invertible operator is bounded by 2 mu. The approximate block matrix operator also will be proven that it's inversible, and its inversible operator is bounded by 2 time n time 1 plus rho n. Now we can see clearly our main convergence theorem of our scheme, taken in consideration that our hypothesis H is satisfied, and that our our initial approximate solution is taken in the bar of center exact solution and radius rho n, where the rho n is taken this value. We can see clearly that our approximate solution is converted to the exact solution for n fixed n, and for only k tend to infinity. In the numerical test, we will consider the nonlinear freedom integral differential equation presented in the work of our colleague Bonaya, where Bonaya here is solved using the DL classical process, discretization using Nystrom, and linearization using fixed point method. So we can see clearly that our LD new process is converged for fixed n, and our result is more powerful than the result of the classical process, DL. And when we see the CPU times, we can see also that our new scheme is fast because it's not taking a very long time to obtain this result, because we have using the speed Newton method. Now we move to the second part of our presentation, when we show efficient numerical scheme for nonlinear integral equation. It will be not LDD method. In the complex Banach space sheet, let's take in F is a nonlinear Fréchy differentiable operator, and in general, as we said in the beginning, that integral differential equation problems are seen as f of c equal the near operator of the space sheet. So let's assume in the beginning that our main problem has a unique solution, and applying the linearization phase using the Newton iterative method, and which our approximate where our solution will be a limit of sequence pk, which given the following linear schemes. And we assume also that our Fréchy derivative operator f prime applying in the exact solution is invertible, and their inverse operator is bounded. Now, secondly, we choose in the discretization phase apply a double projection. So, for the first projection, PM, we will apply in the Frisch derivative operator F prime, only F prime. The second projection, PM, will be applying in the path operator in F prime, and in the second hand of our equation in F. We're taking in consideration that our projection is punctually convergence. And let's assume also that our Frisch derivative operator is lambda Lipschitz, and we taken the value of R, taking the following form. And for L large enough, we suppose also that the discretization process satisfied the following condition. Now, before to sit in our main convergence theorem, we need to sit in some lemma that is verified for all hypotheses H1 to H4 as the following manner. And for the lemma 2.1, it will be used to prove that our approximate operator of the Frisch derivative operator Fn prime minus the inversible operator of the Frisch derivative operator Fn prime is Lipschitz with this value. Let the constant nu, r, lambda, and rho n be defined in the previous lemma. We defined also the constant L such that is the Lipschitz constant of our Frisch derivative operator, Frisch differentiable operator F. And our main our main convergence theorem is sitting as the following form, where as a whole time we taking our initial value in the bar in the neighborhood of the exact solution with a radius rho n, where in this time the rho n taken this value, and we see clearly that our approximate solution is converged to the exact solution for n big enough fixed, and only for k tend to infinity. Now we will see an application of nonlinear freedom integral equation using the Kantorovich projection. Let's see the Banach real space, and let's K be a nonlinear integral complex operator defined as the following manner. We define the Frisch derivative operator of the Frisch differentiable operator K, and we see our problem as the following manner. We can rewrite our problem as the following form. So it's taking the general form of nonlinear functional problem, f of c equals 0. And let's define the order basis en tilde and its adjoint basis en tilde star, and we define the operator projection Pn taking the following form. Now we define some notations in advice to use them to clarify the description of the matrices and the linear combination. And with the previous notation, we can write our Kantorovich projection taking the following expression. So using this notation, our projection of Kantorovich taking the following form. And now we apply the LDD new process that we have explained in the general form. And we get our discretized linear scale represented by 17, and we need to suppose this similar condition that we needed for satisfying the hypothesis of the main convergent theorem. And we recall that the discretization process defined in problem 17 is based on the double projection as follows. And the lemma, by using the lemma 2.y that we have seen for all C in the neighborhood of our exact solution, so the operator E minus T is invertible and its invertible operator is bounded by 2 ni. Here we see this proposition to satisfy the H4 that we have seen in the general form. So if the hypothesis H5 holds, and we suppose also that our projection is punctually our projection it converges punctually to the identity operator, and the seat, the following seat is a relatively compact operator. So we have our approximate operator converge on norm or converge normally to the integral operator T. So this condition is similar to the hypothesis H4 in the general form that we have seen. And by using proposition 2.3, hypothesis H5, and according to lemma 2.1, we can determine that the approximate operator E minus T n of the operator E minus T is invertible, and its invertible operator is bounded. And where R and rho n is parameters defined in the lemma 2.1. So now, at this point, we have satisfied all the hypotheses of our main convergence theorem 2.4, and we can see clearly that our approximate solution of our nonlinear integral operator problem is converged to the exact solution C. For n and fixed, and for k, only k tend to infinity. Now let's focus on the implementation of our LDD scheme. So we remark that our second member term of our LDD scheme taking the following form, and we can write also the following equalities. And accordingly, we can explain, we can write our approximate solution Cn k plus 1 by the following expression, where the xnm k plus 1 here, it's in the space Cn, complex space Cn, and it's a column vector. We find this by solving the following linear system. So xnm k plus 1 is the solution of the following linear system, where Ank and Dnmk, the second part of our linear system, taken the following expression. Now we move to the numerical test. Here we consider the following nonlinear freedom integral differential equation presented in the work of our colleague Khalaf, where Khalaf here solving this problem using also the LDD new scheme, but with a difference discretization phase. In the discretization phase, Khalaf used the Sloan projection, and we, in our work, we use the Counter-Vich projection. So the construction of the system, of the following system, is given as the following manner we use in the first work. So, and we can for the numerical test, for the result, we can see clearly that our LDD Counter-Vich is more powerful than the DL classical process, discretization than linearization, and is more powerful also than the LDD using the Sloan projection, doing by Khalaf et al. And we see also that the time CPU is not very big compared to the DL classical process and the Khalaf work. And now we pass to the third part of this presentation, where we will solve a system of weakly singular nonlinear integral equation using the LND-Canyon method. So in this work, we will trace the following nonlinear type of equation. So this equation is a nonlinear integral differential equation with a weakly singular kernel. And we can see clearly that the singularity is come from the derivative of the function q. So for taking more data on our problem, we derive the problem 21, and we construct our nonlinear integral differential equation by setting the following notation. So, system 24, before we define the product Banach space Xi, and the system 24 can be rewritten as the following system, and the operator K1, K2S, and K2R are the operators presented by the following expression. Now, the main problem we take is find psi that solve this equation. It's writing in the general form of functional nonlinear equation. And we must also derive the Frisch derivative operator T1G, T2GS, and T2GR. Let's be the Frisch derivative linear operator of the operator K1, K2S, and K2R, and it's given by the following form. And we must also define our Frisch derivative operator NT of the Frisch differentiable operator K presented in the main problem. Now let's assume the following hypothesis, and this hypothesis is similar to the hypothesis we used in the last work. And applying the linearization discretization process, we get the following scheme. So, finally, we can give the expression of our approximate solution as the following form. And also here, the x and k plus 1 is the solution of the following linear system that will be take, in this case, the following form. Because we have a system of two equations, A and K will be a block of matrices. And the bracket is represent the duality brackets between the space Xi and its dual space Xi star. Now we need to define each method we will use to estimate our integral represented in our scheme. So for the integral, regular integral, we will use the Nystrom approximation, and for the integral of and for the nonlinear weakly singular kernel operator, we apply the product integration rule for estimate this integral. So for all linear weakly singular kernel Tn and S, we find it in the second equation because our singularity is given from the derivative of the kernel Q here. So we use the products integration rule, where the parameter beta r is given by the following expression. For r equal 1, for r difference to 1 and to n, and for r equal n. So now we can consider that all the operator of the matrices operator MT is a compact operator, and we suppose also that Pn is punctually converged to the identity operator of the Banach space Xi, which MT is defined. So the approximate operator MTn is converged uniformly to the operator MT, applying the theorem 4.1 of Mario-Albers. For n large enough, we can write the following H3 condition. Now we satisfy all the conditions that we permit to us to sit in the following lemma. And now we sit in our main convergence theorem. It takes the same form of the past theorems, where our approximate solution also will be converged to the exact solution for a fixed big N and only K tend to infinities. Now for the numerical test, we consider the following nonlinear integral differential equation, and using the same techniques we do before to construct the following system of equation. And the estimate error taken the following form, and this is the numerical result by taking n equal only 5, and the big N is n of the estimation of the integral operator for the products integral rule. We see clearly that our result we see clearly that the result of our approximate scheme is acceptable. Now we close with the conclusion. So in this research, our main focus was explain and develop a particular type of linearization discretization schemes for effectively solving system of nonlinear Freedom integral equation of the second kind. It introduced a new method called LNDN to solve system of nonlinear integral differential equations, which proved to be more efficient than the traditional approach. And also we have present a numerical method called LDD for solving second-order systems of nonlinear Freedom integral differential equation, which achieved the high precision in the experimental test. Additionally, an algorithm called LNDK was proposed for solving weakly singular nonlinear integral differential equation. In the future, we will plan to use this vision to handle equation over large interval because the possibility of taking advantage of the fast convergence rate of the Newton iterative method and the high precision of the counter-Lubitsch projection. So this is the following. This is the following reference we use to do all this work. Finally, I will thank you for your attention.